Hello, what's up? Welcome back to the stream. Yeah, a 1919 stream on Purescript Graph Comonads. I was thinking about this before coming on, and yeah, it's quite a bit, and I suppose it is a reflection on the fact that there was a lot to do in that Purescript algebraic graph library in order to get to Comonads. So I suppose if I look at my log of why am I doing graph Comonads, ideally we get into maybe some visualization of graphs. That would be really cool. But there's something intermediate, which is this idea of indexed Comonads, or index might not be fractal Comonad, I think is what I want. And I think that's what we want to get at next. I don't know that I don't know that I have a good upper limit on when to stop working on the algebraic graph library, because there is a bunch of stuff there that we could still do, and we haven't pushed in a really long while as well. So I'm thinking it makes sense to maybe just go to 20 and then stop there, and then try and do like fractal Comonads, whatever that is. So let's do a little bit of housekeeping, and let's try and get there. I'll try to make some more progress on our graph Comonads. Okay. So we were trying to work on arbitrary test to check laws, and what that led us to is to see that well, the symmetric closure of undirected graphs is not of an undirected graph is not the graph itself, and that's a problem. And that, I think, points to the fact that we need to have an undirected adjacency map instance, I think. How would that work? I think it would work by having mul being let's see, where are we getting mul from? The internal instance, I think. Isn't it mul? So this one, yes, this one, the semiring instance for adjacency map. And that's almost what we want, but if we do that for an undirected adjacency map, then we need to, I think, also add the symmetric of this. I'm not sure whether that's the most efficient representation. I was thinking about that a little bit the other day, wondering whether this particular representation is somewhat biased. But I don't think we have a better one. A bias in the sense that if we keep track of directed arrows, then of course to make an undirected one, we have to create two undirected arrows. But isn't there an underlying representation where actually in connect is commutative, basically? And but if that's the case, then adjacency map, given that it lists a node and a set of edges, or the set of nodes that it's connected to, seems like biased or unbiased. If we want to do some things like, for instance, finding all the edges of the destination node, then if our canonical form uses something like the undirected one says, like, we only map like the less ordered vertex to all of the other vertices. Then we still need to keep track of the reverse map if you want to do anything that relates to a higher ordered, a greater vertex. So, okay, I think I convinced myself that I just need to create a undirected module where I'll put an adjacency map. Maybe I should look at how Alga does it before embarking on oof, I don't know what that means. So that's FGL. That's also FGL. That's Purescript Alga. Okay, that's base. That's base. It's control monad. That's Alga right there. Okay, so what do I want to check? I want to check undirected. And understand how it's built. Adjacency list. It doesn't depend on adjacency maps. Right, it uses that relation. And then relation has... So hold on, let me delete that. How does this work already? It uses this r.relation, algebra.graph.relation. There's the symmetric relation and the regular relation. And SR does this thing, but basically, as far as I can tell, doesn't use an adjacency map unless relation uses an adjacency map underneath. It doesn't. And now remember that the author, Andre, was saying that that he thought maybe relation should go in another module, a different package altogether. Was this done here? My mouse is not working correctly, and that's very annoying. It was plugged in just a second ago. What could it be? Not that. Undirected. Interesting. It was done by someone else. Yeah, connect does not commute. Implement, that's what I would have thought. But then we do not have adjacency map undirected, but we do have a graph relation symmetric. Let's use it instead. Perhaps adding a to-do that we should really switch to at some point in the future. Ta-da! So I'm on the right track. So let's go back to maybe creating so adjacency map dot undirected. I don't mind doing it that way. So let's do it that way. Yeah, I suppose. Let's keep the hierarchy somewhat close. So that means an undirected purse here and an internal there. It's not the best, but for now, let's do it like so. So that means that this will go in undirected, and it will be undirected here, and we'll re-export undirected.internal, and we'll import undirected.internal. And it feels super duplicatey. Isn't there a way that I can avoid doing that? Let's think about it later. So let's make mul commute by adding this. And I think it kind of should just work, I think. So now if we import agency map dot undirected instead, then my expectation is actually that the tests work, which would be quite impressive if it just does. Let's see, what do we have? G was introduced. So those are warnings. Okay, could not match type. I see. Right. We're talking about a different true adjacency map right now. In the test itself, because we should import the undirected version now as IMU. And on line 130, we need to I think AMU agency list. Oh, yeah, I think so. But it's the 2 UG, that's the problem. Okay, let's go build and let's reload the window because it seems like the checker is not working properly. 134. Oh, okay. It's here now. AMU. Is that right? Probably is. And it builds. Symmetric closure works. Whoa. So hold on. I suppose, yeah, right. Because now the adjacency map is going to require the symmetric of that. Nice. So hold on. I think I need a test for the regular graph, right? Graph Boolean. Don't I have that already somewhere? I thought I had this built, but it's built a simple cycle. Ah, yeah, that's fine. I suppose I can just take those things up there into graph boolean. And the density map, that's going to be like so. And then it's just going to be the, not AM, but it's just to be the symmetric closure of the symmetric closure of the, not the undirected graph, just the regular graph is going to be equal to itself. So is a, so symmetric, what is it? Graph boolean symmetric closure of the symmetric closure is identity. And we want a regular graph, and we want a regular graph here as well. And therefore we want the regular symmetric closure. So graph boolean symmetric closure of the symmetric closure identity. So that didn't work. Why not? Graph boolean. So I'm going to need to show show the adjacency map of G. And show the symmetric closure, the adjacency map of G. Like so, maybe. Except with the parentheses, I suppose. Oh, I need to show that. And I need to show that. And okay. All right, so what do we get here? To agency map of G, take tuple false, false true, double true, nothing. Okay, that's for false, 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 true, false, and false to nothing. Okay, that's not easy to read. And I think I'm going to need okay, I'm going to need some examples, so I'm going to take something like yeah, take something like this. adjacency map G. Okay, and then I'll show am dot symmetric closure of two adjacency G and that. So in this case it's true, so there's really no problem with that. So it seems like I might need to build like a more complex one. Okay, let's try. So for instance, let's try and build this. Or is that let's see if we can find a simpler one. This one looks actually pretty neat. Okay, let's build this one. So this one is what? This one is connect of a disjoint and disjoint, and so okay, so we connect false and true. Which could really be edge false true. And then we overlay that with vertex true. And then we overlay that with vertex true again. And then we connect that to empty. So let's first see whether I get that right. And it looks like this. We might want to log show G as well, actually. Hard to tell. And false true, 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 blah. Yeah, so it's similar except the reverse. So we might not want to do it that way, actually. We might need to do empty connect and then vertex true overlay vertex true. What am I doing? Vertex true overlay vertex true overlay edge false true. Let's try this. Because of course this is a directed graph, so all of the order matters. So what do we have? We have the order matters, but so does the associativity. And written like so, we're not doing these things properly visibly. Let's try like that. And here we have unit connected to appearance of true with appearance and true and then false true. So that's right. And then here we can see that two adjacency map G is this guy with the empty node here, but then the symmetric looks pretty much the same but with the false now in there. Did I misunderstand what symmetric closure was? I think I might have. But that's good. I'm not testing the code, I'm testing my understanding as well. And obviously you want to try and not test all of these things at the same time, but it still allows to falsify one or the other. Compute the symmetric closure of a graph by overlaying it with its own transpose. Yes, there is indeed no reason that that this would hold true for a directed graph. What we want is to transpose, maybe. Let's try and see whether transpose is where we want. am.transpose, I think. And see whether that will work. You'd think there would be a transpose function for graphs, which there is. But let's just double check. And that's, so is it correct? False, true, true with nothing. And now false is not connected to anything. And true is connected to false. So I see how that's transpose. It's not reversed though, is it? No, it is. It is, but let's use transpose directly and let's make a test for it then. So it's the transpose of the transpose is identity. And we should be able to say G equals AM, or actually not even AM, should be able to say transpose of transpose G. And we can leave the extra text for now and we'll just remove it. We don't import transpose. Well, that's fine. Or is it that it's coming from several things? No, it's just unknown. Okay. So that's from algebra.graph. And go. So transpose or transpose is identity. And we have one. Okay. So I suppose what happens is that transpose of an undirected graph should be the undirected graph. But yeah, so let's actually give that a shot. So if we say ug.empty and ug.connect and ug.vertex overlay and so on, and now we say ug.toAdjacency map and amu.transpose, then what do we get? Yeah, that's not gonna work. What's not saved here? that is, oh, maybe because I saved just as the test was finishing the race condition here. Indeed. Okay, so we have our thing, and yeah, transpose is exactly the same, because, and that would make sense for the AMU, given how we've defined it. Oh, by the way, this is wrong. Did I miss? Yeah, I think I must have reverted my show instances or inverted my show instances, because this should in fact be, oh no, hold on, that is the directed version. So what's going on with the undirected version? It's how come G should be undirected here? Why? Why am I getting this result? Doesn't make sense. Doesn't make sense. Directed show instance goes underneath the UG. Ah. So here I would only be able to represent the top level connect as a UG, as a bidirectional arrow here, because after that I'm digging into the P and the Q's, which contains the regular graph. Well, that's not good. But I don't know how to change that. Unless I wrapped Q in UG. Q and G in UG, which is really weird, but this is the pretty printing, right? I think we're okay. I mean, there's this rule that show instances should be readable, but let's try this. There we go. Okay, so we fixed our instance. And our tests pass, but we have the structural equality though doesn't pass. So let's try and see if we can fix that. Structurally equal, G was shadowed. Structurally equal if it is equal. Yeah, no, we know that's not the case. Exactly, we know that's not the case. It's really about the simplification. So, okay. Is there a way to formulate this as, because I think the reverse is there exists a, it's not that structural equality graphs that are structurally equals always are equal. It's that they're the logical negative here is something like there exist graphs that, well, both graphs that being equal are structurally equal, and but there's really no relationship really between the structural equality. Maybe there's a logical implication here, is that if G and H are structurally equal, then they're equal, which we can, I think, encode where is it, modus ponens, no? Like the logical, I think we can convert that into some logical equality if we don't have implication. Which would be if graph is structurally equal to H, which means this is true, something like that. We don't have an imply combinator, do we? We don't. Logical, is it modus ponens? Implication, elimination. If P then Q, P therefore Q. And so P imply Q. Right. So I think we need an if there here. Haskell, write implication as equality. Haskell implication. Implication notebook properties. The for calculus is false. Would be nice to have this, no? Implication in the resulting property holds if the first argument is false, in which case the test case is discarded, or if the given property holds. Skew test case distribution, consider using cover to make sure that your test data is good quality. Interesting. Yeah, I kind of want that. Shall we submit it to, shall we do a little rabbit hole and go into test.quickcheck and find and try and submit implication? Implication. Imply. Implies. It's not there. I mean, as far as I can tell. Let's see, Purescript, because there might be another framework for property testing. Just last year. Learning repo. For quoi type class you type programming? Huh. Oh, that's interesting. So is that trying to test the world? I think it is. It's trying to make sure that laws are valid. Checking these type classes on a on a proxy. So EQ, given the proxy, does a gen with the type, and check EQ gen checks 1,000 times reflectivity and so on. That's pretty cool. It's pretty cool, but it doesn't give us implication. Let's look at how implication is coded. It just discards if false, and if true, it's P. So I think I was going somewhere with my if. I think it's if blah, then blah, else. Discard, which doesn't mean anything. It means just carry on, right? Which I don't know if we have that here. I suppose we can say assert true. There is no discard. That would also be helpful. because right now I'm going to need to do assert equal true true, or I could give a result. Ah, yeah, if I give a success, I suppose. That should be fine. So else success. From test or quick check. Good on hashtag result with tag boolean. Oh, yeah. Right. Right. So what are we saying here? Oh, maybe we're just saying true, actually. And equalities, yeah. So is structure equals implies is equal. And here we're manually coding imply logical implication as if P then Q else true. P Q yeah. And then undirected graph boolean. What is this? Adjacency map of a simple boolean graph. Ah, yeah. That we can fix because the adjacency list of an undirected graph now will in fact not be like so. It will be, yeah, false, false, but no, it will be false, true, false, and true, false. Yeah, false, false, true, and true, false, yes. And that should lead us to only one failing test, which gets us back to our Comonad pointed graph, and that's what we'll do next time. Yeah, I wasn't sure why this didn't work. Yeah, that was really weird, right? And we got a little bit into a oh yeah, actually, if I do this extend extract, oh, you need an arbitrary instance for pointed graph. Well, that's good, because that will give us a minimal example where the law doesn't work, which is what we want. So let's we fixed the symmetric closure equality law for indirected graphs, and now we need to do an arbitrary instance for pointed graph. So we're back into this. Perfect. Excellent. Thanks a lot for watching, and I will see you on Thursday. Bye bye.